Hello students, in the last class we discussed about the oxidation states. The transition elements show variable oxidation states, and also we know the reason for that one due to comparable energy difference between n minus 1d and ns orbital is very small, hence they show variable oxidation state. In this class we can discuss about the magnetic property. The transition elements exhibit two types of magnetic property considered as diamagnetic property and paramagnetic property. The transition element shows two types of magnetic properties called diamagnetic and paramagnetic. The diamagnetic property, it is due to the presence of paired d electron that is having d10 configuration. Paired d electron or presence of vacant d orbital means d0 configuration, either d10 or d0. If they have d10 or d0 configuration, they always shows the diamagnetic property. These diamagnetic compounds, they are repelled by the magnetic field. They are repelled by the magnetic field. This is about the diamagnetic compounds. Diamagnetic property, it is due to the presence of paired d electron that is having d10 configuration, or presence of vacant d orbital that is having d0 configuration. Diamagnetic compounds, they are repelled. If they are placed in a magnetic field, from the magnetic field they get repelled. This is about the diamagnetic. Then paramagnetic property, it is due to the presence of unpaired d electron. Unpaired means having d1 to d9 configuration. d1 to d9, any d1 to d9 configuration, those are generally paramagnetic in nature. These paramagnetic substances, they are attracted by the magnetic field. Paramagnetic property, it is due to the presence of the unpaired d electron. If you paired electron, then it is diamagnetic. Unpaired means generally having d1 to d9 configuration. They are weakly attracted. They are generally weakly attracted by the magnetic field. Then one more special property is the substances which are strongly attracted. If they are weakly attracted, they are paramagnetic. If they are strongly attracted by the magnetic field, such magnetic property we are called as the ferromagnetic substances. Ferromagnetic substances, it is a ferromagnetism, which is a special property of the paramagnetism. If they are strongly attracted by the magnetic field, those are called as the ferromagnetic substances. Ferromagnetic property generally shown by the iron, cobalt and nickel. Iron, cobalt and nickel commonly shows the ferromagnetic nature. Then this paramagnetic property, already it is studied that it is due to the presence of unpaired electron. Paramagnetic property, it is due to the presence of the unpaired electron. Paramagnetic property is due to the presence of the unpaired electron. Each electron having a magnetic moment. Associated with that magnetic moment is due to associated with orbital angular momentum. Orbital angular momentum and spin angular momentum. Spin angular momentum. Each electron having a magnetic moment. Each electron having a magnetic moment associated with its orbital angular momentum and spin angular momentum. This orbital angular momentum is effectively very small. It is small and is of no significance. We are ignoring the magnetic moment due to orbital angular momentum because of its effectively small nature. Then that magnetic moment generally denoted by the symbol mu. The magnetic moment is determined by the number of unpaired electrons. Magnetic moment is determined by the number of unpaired electrons and can be calculated by using the spin-only formula. Magnetic moment can be calculated by using the spin-only formula given by mu is equal to root of n into n plus 2. This is the spin only formula, very important. The magnetic moment, it is calculated by using number of the unpaired electron that can be determined by the number of electrons by using the spin only formula because orbital angular momentum is neglected. Then by using spin angular momentum, you can calculate the magnetic momentum. Hence, that magnetic momentum is determined by the number of unpaired electrons and is given by the spin only formula. That spin only formula, it is given by root of n into n plus 2, where n is given by the number of unpaired electrons. Then the unit of that magnetic moment, it is given by Bohr magneton. That is given by the symbol Bm. Bohr magneton. As the number of unpaired electron increases, the magnetic moment also increases. The unpaired electron, with increase in the number of unpaired electrons, magnetic moment increases. In some cases, if they can consider if the magnetic moment of an element is 0, indicates that it has no unpaired electron. That has D0 configuration. Due to absence of the unpaired electron, its magnetic moment can be 0. As the unpaired electron increases, magnetic moment also increases. By using this spin only formula, you can calculate the magnetic moment. For example, you take few examples. For example, you take scandium 3+. To first consider the electronic configuration. The scandium electronic configuration is 3d14s2. Scandium 3+ means the 3d04s0. You have to remove the 3 electrons. 3d04s0. Hence number of unpaired electrons equal to 0. If n value no unpaired electron, then magnetic moment given by the formula root of n into n plus 2. N means the number of unpaired electron. That means 0 into 0 plus 2. Anything multiplied by 0, hence you get 0 Bohr magneton. Scandium 3+ has 0 Bohr magneton because it has no unpaired electron. Like that, you can calculate for any ion. For you take another example like that is titanium 3+. Titanium 3+ means the titanium configuration is 3d24s2. Titanium 3+ means you have to remove 3 electron First remove the electron from the 4s orbital, then 3d1 4s0. Here one unpaired electron present, n value equals to 1. Then magnetic moment will directly substitute the value, n value equals to 1. 1 into 1 plus 2, that means you can write root 3 Bohr magneton, or you can simplify the root 3 value. Like that, you can take other examples, like for example Cr2 plus. Calculate the magnetic momentum of the Cr2 plus. First you write the Cr configuration. Cr means the 3d5 4s1. Cr2 plus means the from the 4s 1 electron, from the 3d 1 electron, means that becomes 3d4 4s0. 3d4 4s0. 3d4 means you consider the box diagram. That is 1, 2, 3, 4. This is the 3D. D subshell has 5 d orbitals. According to Ohm's rule, you have to fill the electron. Hence, n value equals to 4. N value 4 unpaired electron. Hence, magnetic moment mu equals to 4 into 4 plus 2. 4 into 4 plus 2. That means magnetic moment equals to root 24 Bohr magneton. Root 24 Bohr magneton. Similarly, you take one more example like Fe3 plus. Fe3 plus magnetic momentum is given by iron means 3d6 4s2. Fe3 plus means you have to remove the 3 electron, 2 from the 4s, 1 from the 3d, that becomes 3d5 4s0. 3d5 means according to Ohm's rule, you fill the electrons. That is, it has 5 unpaired electrons. N value equals to 5. Then root magnetic moment, root of 5 into 5 plus 2, that means root 35 Bohr magneton. Very important one for the 2 marks. They can take any ion like that. Zn2 plus means 3d10 4s0. Zn means 3d10 4s2. Zn2 plus means 3d10 4s0. That means n value for this one becomes 0. Why it is 0 means all are paired electron. For example, this is paired. All are the paired electron. N value 0. N value 0 means magnetic moment also become equal to 0. Like that, you can calculate the magnetic momentum for other ions also. You can practice for number of the 3D series element, that is scandium to zinc. From scandium to zinc, they can ask any ion. One more example, for example, nickel 2 plus. Nickel 2 plus means the 3d8 4s0. 3d8 4s0. Nickel 3d8 4s2. Nickel 2 plus means 3d8 4s0. 3d8 means you take the box diagram. This is the 3d8. 3d8 means n value it is equal to 2. N value equals to 2. Then magnetic moment mu equals to 2 into 2 plus 2. That is root 8 Bohr magneton. Root 8 Bohr magneton. This is about the magnetic momentum. For example, you take Cu2 plus. Cu2 plus means the 3d9 4s0. 3d9 4s0. Cu means 3d10 4s1. Cu2 plus means 3d9 4s0. N value for this one according to box diagram. These are paired. Up to here paired electron. Only one unpaired electron. 3d9. N value equals to 1. Then magnetic moment equals to root of 1 into 1 plus 2. That means root 3 Bohr magneton. Root 3 Bohr magneton. For Cu plus, what happens to the magnetic moment of Cu plus? Cu plus means 3d10 4s0. 3d10 4s0 means n value equals to 0. If n equals to 0 means magnetic moment also equal to 0 Bohr magneton. Out of Cu plus and Cu2 plus, which one is paramagnetic, which one is diamagnetic? That is, Cu plus means 3d10 4s0. This is said to be the diamagnetic due to paired electron, while Cu2 plus it has unpaired electron, hence it is said to be the paramagnetic. These are all very most important one. Then in the competitive exams, they can give the magnetic moment. For example, magnetic moment mu equals to 1.7 Bohr magneton. How many unpaired electrons are present? How many unpaired electrons? If they are given like this, if they given magnetic moment, by using magnetic moment, you have to calculate the unpaired electron. Unpaired electron. This is important for the competitive exams. 1.7 Bohr magneton means you find out the unpaired electron, that n value always equal to 1. 1.7 means n value equals to 1. If you take n value 1, root 3 value is equal to 1.7 Bohr magneton. Similarly, you practice other example. For example, magnetic moment equals to 2.8 Bohr magneton. How many unpaired electrons are present means directly you can write n value equals to 2. Based on this magnetic moment, if they are given 2.8, then n value equals to 2. You calculate that n value 2, you get only 2.8 Bohr magneton. For example, n value magnetic moment equals to 4.8 Bohr magneton. Then how many unpaired electron means directly you can write n value equals to 4. You take the decimal point left side digit, that gives the number of the unpaired electron. For example, magnetic moment mu equals to 5.9 Bohr magneton. 5.9 Bohr magneton. Then what is the number of unpaired electron? Unpaired electron, it is equal to 5. Without calculating, directly write the number of unpaired electron. This is very important for the competitive examination. This is about the magnetic moment. Then among that configurations, for D5 configuration, you take that D5. D5 configuration only contains the more number of the unpaired electrons. For D5 it has 5 unpaired electrons, hence D5 configuration has maximum magnetic moment. Highest magnetic moment is shown by the D5 configuration. D5 configuration. Then you take the scandium 3 plus, titanium 4 plus. These scandium 3 plus and titanium 4 plus, these are taken as the diamagnetic in nature. They are diamagnetic. Why they are diamagnetic means, for scandium 3 plus and titanium 4 plus, you get D0 configuration. It has no unpaired electron. Hence, they are said to be the diamagnetic. Or you take Zn2 plus, Zn2 plus or Cu plus. These are also said to be the diamagnetic. Why they are diamagnetic in nature means they have D10 configuration. Again, they not contains any unpaired electron. They have the paired electrons. D10 means no unpaired electron, only paired electron present. Hence, these salts are also diamagnetic in nature. While you take Cu2 plus, Cu2 plus means it has a D9 configuration. Due to D9 configuration, it is said to be the paramagnetic. Paramagnetic means that is weakly attracted by the magnetic field. They can ask like that also. Out of Cu1, copper 1, Cu1 and Cu2. This 1 and 2 generally indicates the oxidation states. Oxidation state. Cu1 nothing but the Cu plus. Cu2 nothing but the Cu2 plus. Out of copper 1 and copper 2 salts, which is paramagnetic, which is attracted by the magnetic field, which is repelled by the magnetic field. Like that also they can ask the question. Copper 1 means it has D10 configuration. Copper 2 means it has D9 configuration. D10 means this is diamagnetic. Diamagnetic means it is repelled by the magnetic field. D9 means it is paramagnetic in nature. Paramagnetic means it is weakly attracted by the magnetic field. For any type of the ion, you have to first write the configuration. If it has D0 or D10, they are diamagnetic in nature and they are repelled by the magnetic field. If D1 to D9 configuration, they are said to be the paramagnetic and are weakly attracted by the magnetic field. This is about the magnetic property. And one more, among these copper 1 and copper 2, Cu plus, and very most important, even in the CET 2020 they take this question, out of Cu plus and Cu2 plus, that is they are given like this, CuCl and CuCl2. CuCl means this is plus 1 oxidation state. CuCl2 means plus 2 oxidation state. Out of CuCl and CuCl2, which one is more stable? Which one is more stable? Generally, in first year syllabus, it has a D10 configuration. This is said to be the more stable in nature. D10. For Cu plus, you can write D10. For Cu2 plus, it has a D9. According to first year syllabus, that Cu plus is said to be the more stable. But generally, compared to Cu plus, Cu2 plus is more stable in nature. It is very most important. Why Cu2 plus is more stable than the Cu plus means the Cu2 plus have very high negative hydration enthalpy. Due to very high negative hydration enthalpy, Cu2 plus is more stable than the Cu plus. You have not take the configuration. You don't consider the configurations D10 and D9. According to configuration, Cu plus is more stable than the Cu2 plus. But generally, Cu2 plus more stable than the Cu plus. Why Cu2 plus is more stable than Cu plus means due to its high negative hydration enthalpy, Cu2 plus is more stable than the Cu plus. That means out of CuCl and CuCl2, CuCl2 salts are more stable in nature. This is very most important. This is about the magnetic property. In the next class, we can discuss about the color property.